Hello everyone, welcome to the lecture series on foundations of algebraic structures and number theory. In today's discussion we are going to talk about quadratic Diophantine equations. So in number theory already we have discussed about what is Diophantine equation and what is linear Diophantine equations. In today's discussion we are going to talk about quadratic Diophantine equations. In quadratic Diophantine, you know the general form of it, x square plus y square equal to n model. So as I said in linear, here even we can check whether this given equation is solvable or not. So a quadratic Diophantine equation like x square plus y square equal to n can be solved by representing the numbers as sum of the squares. Since it is a square model, so we can find the solution by representing the numbers as sums of squares. So here the condition for representability is given as below. A number can be represented, that is, it can be expressed as a sum of two squares if each prime factor of the form a, that is 4k plus 3, appears with an even exponent in its prime factorization. I repeat, a number can be expressed as a sum of two squares if each prime factor of the form 4k plus 3 appears with an even exponent in its prime factorization. So you can see one example here. I have stated an example. You have a quadratic Diophantine equation, x square plus y square equal to 25. 25 is the n value. So the solution include the structure 5, 0, 0, 5, 3, 4, 4, 3, and their negatives. So in this for this particular equation, we get these kind of sets of solutions. So the next is higher order Diophantine equations. So higher order Diophantine equations are like x power n plus y power n equal to z power n model. So Fermat has discussed something on the higher order Diophantine equations. Fermat's last theorem, what it says: the equation x power n plus y power n equal to z power n, where n is greater than 2 has no integer solutions. It has no integer solutions. And this famous conjecture was proved by Andrew Wiles in 1995. So actually this was told by Fermat and it was proven by Andrew Wiles in 1995. So its significance: Fermat's last theorem has had a profound impact on number theory and has inspired numerous developments in abstract algebra and algebraic geometry. So what Andrew Wiles says is we can use this Fermat's last theorem for advanced technologies and like from elliptic curves and model forms. You know, elliptic curves are used in cryptocurrency areas. So elliptic curves and modular forms showcasing the deep connections within mathematics. It's a very good approach. It can be connected in between mathematical domains. So that is how it could be interlinked with different areas. So according to Fermat's last theorem, the connection between the x variable and y variable and z variable shows that there cannot be integer solution of such kind of equations where n is greater than 2. Maybe for example, you assume you have an equation x cube plus y cube equal to z cube, or x power 4 plus y power 4 equal to z power 4. In that scenario, if you work on, if you try to solve and if you try to get the solution, you won't get integer solutions. That is what is told by Fermat, and it was proven by Andrew in 1995. And again, it has a very good significance, very good importance in the recent advancements in technology. So thank you for listening. Thank you.